Hi, thanks for the introduction. I've called it Hadoop now, so at the end of the talk we'll have a vote, and you guys have to tell me whether it should be with Hadoop and PHP or with MapReduce and PHP. I'll explain what Hadoop is and what MapReduce is in a second. My name, as already said, is David Zuelke, and the weird dots over the name give away that I am indeed German, but that shouldn't frighten any of you because we're all friends now. All differences forgotten, right? So, I'm from a beautiful city of Munich, as was already said, which is most famous for the Oktoberfest and the good beer that comes from there. I work there as a founder of a company called Bitextender. We do scalability, system architecture, web stuff, Hadoop, among other things, a lot of REST. I give a lot of REST talks, for instance. I'm also the lead developer of the Agave framework, which is awesome. This is my Twitter nickname if you want to bash me or praise me while I'm giving this talk, if the internet works, which I think it doesn't, because this is not Germany. No, just kidding. It also breaks down in Germany. Curiously, here's the fun thing. The only conference I've ever been to that was reasonably large with an internet that didn't break down was Belgium, of all places. So, I have a lot of slides, so I'll go through them and explain stuff, and then there's a hands-on. And the hands-on will be a complete disaster. It'll be my Waterloo, right? Because I've written this cardinal sin. It's new code. I haven't tested it. 5 minutes ago, I was literally just hacking away on it, and I don't think it'll work. But we'll see. So, an overview of like what distributed and parallel computing requires is this part of the presentation. The key challenge we face, well, I'll assume, is we want to process data, right? Lots of it. But how much is a lot? This is the first question. Here's some numbers that are really outdated because these companies in question don't publish them all the time. So they are like a year old. But Facebook gets a lot of new data per day. In 2007, 2008, that was 200 gigabytes of data, like logs, new statistical information, new data metadata about people they had to process and somehow make sense of. But they are rapidly growing, as we all know. So by April 2009, it was 2 terabytes a day, 10 times this amount. And it was 4 terabytes by October, and it was 12 terabytes by March 2012. So they've grown from 200 gigabytes a day to 12 terabytes a day, which is lots of data. And Google, they process 400 petabytes a day, a month. That was in 2007. I haven't seen more recent numbers since. And the average job size for them is 180 gigabytes. This MapReduce approach that I will be showing is something that Google used to use to produce their index. Yahoo still uses it to build their search index. Google have since moved away from it. It is still a very, very cool thing. And as you can see, Google takes this massive amount of data and they chunk it up into smaller slices, and then they process these smaller slices. But what if you have that much data, right? Let's say 1%, just 1% of this amount that Google had or Facebook had a long time ago. So you say 2 gigabytes. Maybe, let's say you have 50 gigabytes, okay? You say that's no problem. Here's the cool thing about this. 180 gigabytes, the average job size that Google does, is going to take you 45 minutes to read off a hard drive. SSDs don't really change that because what you want to achieve in the end is just I/O, is throughput, which means you'll have RAIDs, okay? So, and then at some point the interface, you reach the peak bandwidth of the interface. It's really annoying. It blinds me. Can you switch off the spotlight? Is that possible? Thank you. Ah, hello, I see you now. Good. So this is the challenge, like the I/O, right? You want to read sequentially because that's faster. Because at the scales at which these guys operate, buying SSDs is still a little bit expensive. Even though Facebook not, but Google have too much money on their hands and they don't know how to spend it. I guarantee you that if they bought SSDs instead of hard drives, that would be expensive even for them. So you have big amounts of data that takes a long time to read. And then you have the problem that maybe you have 16 gigabytes of RAM per computer. Maybe you have 64. It doesn't matter. The whole data set that you want to process does not fit into memory, typically, right? And in general, nowadays, computers can process data orders of magnitude faster than they can read it. Computers nowadays are I/O bound, pretty much in all cases. Unless you're doing have a computing cluster at some kind of university, like folding molecules to do cancer research, which is really, really, really computationally expensive. And then you move the complex jobs to run on the GPU or something. But we as web developers, we don't have these cases typically. We deal with data. And we need to, as a solution, the only way to speed things up is have parallel processes that do this, right? So you don't have one computer that performs these operations, but you want 100. But the problem is that once you do this, you need to start coordinating what you're doing, right? You need to somehow organize what computer does what, keep them in check, make sure that the results are fine, that everything is orderly and German and works. But that's hard. That's really hard. What if a node dies? Like one of the, you write some sort of like custom code, maybe with Gearman or something, and then it runs in the background and blah, and moves stuff to other computers. But then one of the computers breaks down. For Google, every minute a computer probably fails in their data centers. Google, when a hard drive fails on Google server, they don't replace the hard drive. They just switch off the computer. They can't be bothered. It takes way too long. They have shipment containers that are full of computers. Computer fails, they just leave it dying. That's fine. But in that case, if this computer was processing a small amount of your data, another computer needs to take over, right? But then you have I/O again, because maybe that computer needs to read the data from somewhere, et cetera, et cetera, et cetera. So if this node dies, the data, is it lost, right? What happens then? What about the other nodes? Does the whole process have to restart, or can you live with just this one part of the job failing, and can it be restarted? And how do you coordinate this? That is MapReduce. Well, not kind of. MapReduce is the approach, and implementation will coordinate it for you. But the idea is that many years or decades ago, when large computer clusters were mostly, or mainframes were mostly run by people with really long beards, you would distribute the workloads across a grid, right? Because that was the times when there was not a lot of data, but still computationally expensive tasks. One thing would be weather forecasting. You mostly crunch numbers. You have input for that, sensor data input, etc. But there's so much statistical stuff, and you need to do like the algorithms. They are CPU intensive. That worked very, very well in the olden days. You had like Beowulf Linux clusters, right, and stuff like this, supercomputers. But they ship the data around between nodes, okay, which was typically stored centrally on like a storage-attached network and a network storage of some sort. And that is an I/O bottleneck, as we already figured out, because it'll take so and so long to read it off a disk. A disk has a really fast interface, and then you need to ship it over gigabit Ethernet, on which other communication is also happening. Then you have fiber channel and all these things, but that costs lots of money. What you actually want is off-the-shelf hardware in a network, and it'll just be blazing fast. So in 2004, Google, they had this publication called Simplified Data Processing on Large Clusters. They called it MapReduce, because it's built fundamentally on these two map and reduce functions of that functional programming languages so love. We'll look at it in a second. And the key is that now the data is spread out across the computers in a distributed file system, and you move the processing jobs to where the data already is. Because moving a few kilobytes of code in place on every computer and then starting is much cheaper than shuffling 50 gigabytes of data around when a node dies. You simply tell a node that also has the data of the other node that failed, restart this job. You need redundancy in the storage, etc., but we'll cover that in a moment. And the cool thing is, this is key to scalability. This is actually something that modern network, who's a CouchDB user? Who has you heard of CouchDB? Oh, quite a few people. You guys rock. Who's a MongoDB user? My condolences. It's a crap database. But so CouchDB. No, really, it is. I keep saying it's designed by a committee of clowns and stuff, but I can tell this story later. So CouchDB is a really good example for the trade-offs that we have learned to make in recent years. See, it's particularly difficult in Germany to sell to a manager that something might go wrong. Like, oh, the data might be gone. Like, we might lose 0.01% of the data per day, and they will say, nein, 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 das ist verboten. You must not lose data. But if you want to scale up, you cannot have everything in sync. You cannot notify everything that something happened. Like, the web is the best example. The reason why the World Wide Web became the first planetary scale computer network that there has ever been is the link, the hyperlink, and more generically, hypermedia. Because you can link to another resource, and if that resource is gone, you'll get a 404 from the other server. There is no mechanism that when a resource is deleted on the web, all the links that point to it somehow get notified that something happened. There is no locking on the web. That is why it works so well. This is the only reason why it became successful. But what we have in MapReduce is basically it's the same philosophy, it's the same approach. You have a share nothing architecture. Individual nodes on this cluster do not know anything about other clusters, other computers. So you have 100 computers, each working on a small chunk of your data processing job, right? But they are not aware that there are 99 others. They don't know how far along the process is on these other computers. It's a share nothing architecture, which dramatically decreases the amount of coordination you need between computers, and that allows scale. Because whether you do this with 10 or 1,000 nodes, doesn't matter, it'll still work. Unlike other technologies where at some point the cost of communication between nodes becomes so expensive that you can't afford scaling up anymore. The basic principle is that a mapper first reads a record, let's say an Apache log file, okay, and extracts a key and a value. And if each line in the access log is treated as a record, then we would say read the client IP address, okay, and use that as the key, and we use the number of bytes that were transferred in the request, because that's in an Apache log file, right? You've all seen Apache log files, hopefully? Cool. But you gotta ask. And we emit that as value. So we have localhost, 10 bytes. Some other IP address, 150 bytes, et cetera, okay? And this gets emitted. And the cool thing is, like, a very basic approach of splitting up this workload across many computers would be you rotate logs in such a way that you have one log file per hour, and then you can have 24 computers working on analyzing the data for one day. In practice, it's much better than that. The Hadoop distributed file system actually is aware of the nature of the file. So it says, okay, there's a text file, it's splittable, and it'll split it up into smaller chunks. So you can have one big log file, but it'll still be able to do this in parallel on more than one instance. So now you have a lot of IP address, number of bytes, IP address, number of bytes, lines, essentially, right? Let's say, across a few files. And then you bucket them into one bucket per IP address. So the key becomes essentially the collection. This is then handed to the reducer. The reducer receives this key, the IP address, let's say localhost, and all the number of bytes that we received. And the cool thing is, this step requires some coordination. So you have 10 computers doing this, right, producing IP bytes, IP bytes, IP bytes, and then it'll collect all the byte numbers for one IP address on one computer. And then there you can sum them up, and then you know which clients across your cluster of 100 web servers, which clients did the most traffic. You can also do this with the request URL, which would be much more practical, but this is just an example. So we sum this up, and if you look at this step by step, if you assume that this is your input, okay, then you have a few IP addresses. I have a laser. IP addresses and byte. Awesome, right? I wish this looked like a shark with a friggin' laser beam, but so you have IP addresses, and so this is just two different IPs, but as you can see that there's no order, right? Because it's an Apache log file, and then you can group it like this, okay? And now you can send this off to one computer and this to another. And what they do is they take all these bytes and sum them up. Boom. That is trivial, right, if you do it on one computer. If you have 100 web servers, you could ship it all to one box, which takes forever because there's a couple of gigabytes per log file, for log files per web server. If you have 100 web servers, you have a lot of traffic, I suppose. That's just I/O, I/O, I/O. So this is the thing that MapReduce and its implementation Hadoop solves. We're going to look at that later, if my code works. So if you put this into code, it kind of looks like this. You have a map, okay? You get the line number and the line text. The line number is not really important. It could also be a byte offset, or maybe just ignore this because with treating text files and having a key for the mapper makes not a lot of sense, but Hadoop does it anyway. So we parse the Apache log and we say, okay, this returns some sort of array. This is an imaginary function, right? So we have the IP and the bytes. So we use the IP as the key and the bytes as the value. And then some magic happens, and then our reduce function is called with a key and an array of values, and we do an array sum. This is actually bad, because the problem is you'd have to load all values into memory. So better is to have an iterator that doesn't have to do this, but this only affects when you do PHP. The Java stuff that Hadoop comes with doesn't have this problem anyway. But this is what you use as input, okay, basically. And this would be the output. If this was sorted, we could actually just read from standard in and emit to standard out, and read from standard in and emit to standard out here, and then use Unix pipes. I could demonstrate this later if you want. But theoretically, that would work already. You could just cat the file into the mapper, pipe it out into the reducer. The only problem is that the keys do not get grouped in the step between that, so you wouldn't get this exact result. But this is the result that you get in theory, okay? So IP address and the sum of bytes. Hold on. Broken slide is broken. What did I do? I'm just deleting slides that make no sense. Okay. So now to do all this, I mean, MapReduce that's just an idea, right? It's a system architecture of sorts. But you want to implement something using this approach. For that, you use Apache Hadoop. It's a yellow elephant, so it's Java, but still, it's an elephant. It is a MapReduce framework, which actually also has a massive, massive, massive ecosystem of auxiliary projects that somehow complement this general MapReduce idea. You have a distributed file system, you have stuff for serializing data, you have systems that are able to coordinate distributed workloads, all these things. It's really, really cool. And what Hadoop essentially does is it allows us, it does all the heavy lifting, the coordination of jobs, the sending data back and forth if necessary, the distributed file system, so we can focus on writing mappers and reducers, okay? And it works extremely well, because if you look at some of the users, for instance, Facebook, they use it mostly with a technology called Hive. Hive essentially, what you saw earlier, we emitted IP, tab, number of bytes, right? With Hive, you can treat that essentially as a SQL table, and then make SQL-like queries against it, and it'll transform this SQL into mapper and reducer code, compile it, ship it out to clients, and do stuff, and like an hour later, it gets back to you with a result. So with MapReduce and with Hadoop, you don't get instant results. The stuff that I showed you, if you want to do it across 100 web servers with many, many gigabytes of logs, it's probably going to run for an hour or two, okay? But you can speed it up. If you want to run it twice as fast, you can just add a bunch of processing servers. Ideally, you run Hadoop on each of your web servers, at least a distributed file system, because most web servers do not really have a high amount of CPU utilization, so they are oftentimes idle anyway, so you can give them something to do by installing Hadoop instances on them. Facebook, most of their tasks are Hive, so it's SQL, but the basic principle is the same. They have 8,400 CPU cores with 12.5 petabytes of combined storage. That is also at least a year old, this number, so it's a lot. I suppose it's, that'll be 4,100 servers, I guess, 4-core servers. I'm sorry, 2,100. Yeah. Oh no, actually it isn't, because it says here 8 cores, 12 terabytes of storage, sorry, and 32 gigabytes of RAM per node. Okay. They have, and here's the cool thing, they have gigabit Ethernet for each server in a rack, and each rack has 4 gigabit Ethernet, like a trunked connection, right, with four lanes to from the rack switch to the core switch. And this is a key thing, because Hadoop is aware of your network topology. When you say, hey Hadoop, I have 10 computers, you can actually tell it, these 5 are in a rack and these 5 are in a rack. So when you store data and you say, I want a replication factor of 3 for the data I store, for data safety and in case something fails that other nodes can take over, it'll store the data on a server, it'll store a copy of the data on another server in the same rack, and then it'll store a third copy of the data in a rack that's as far away as possible in case something blows up, right? So this is pretty cool because they essentially rely on the fact that if there's data that one node needs, it can copy that locally. But if data needs to be shuffled around between nodes, many nodes need to do this at once. So they have, like, the backbone across the racks has a higher capacity. They do 25 terabytes of logging data. This is what they ingest with a technology called Scribe. Scribe, has anyone ever heard of Thrift? A few. Has anyone ever heard of Scribe? Have you used Scribe? Did it make you angry? Good. Have you heard of Flume? Cloudera Flume? It's perfect. Okay, I'll talk about this later. So Scribe is essentially a log aggregation service. What it does is you start like a listener on each box, on each web server, and you make this is a local socket connection through a protocol called Thrift. Thrift is like Google's protocol buffers. It's a serialization format. You can use it to do RP remote procedure calls, and so you have like code that logs from like a PHP code or Java or whatever. It uses this Thrift interface because the Scribe interface, it says there must be a category for the message and a message. There's no timestamp, which is very clever. And and then you can say, okay, so this is a service definition and I want to generate code for PHP or Java or C++. And then you have generated code that can simply log stuff to this service. This service means it's a local agent on every box. If you have 100 web servers, you have 100 local agents. You log to them. They buffer the stuff on disk in the background, and occasionally they will send the stuff to a central Scribe log aggregation server, which is very cool because the logging calls that you make from your PHP web server software, for instance, they are non-blocking. They return immediately. And then after a while, the data will end up in some sort of central storage system. They put the data they collect with Scribe into HDFS, into Hadoop's distributed file system. The Flume is like an alternative product that I'll cover later, which is much more modern, has a much nicer architecture, and is better suited to that. But anyway, they have 25 terabytes of data. And they scan 135 terabytes of data, roughly, a day with their processing jobs that run. They touch 135 terabytes of compressed data, because everything's gzipped in Hadoop, typically. They run around 7,500 Hive jobs, and these together consume about 80,000 compute hours per day. And the new data they have is 200 gigabytes per day in 2008, 2 terabytes in 2009. I think I already showed you this. Yeah, that was in an earlier slide. Yahoo, on the other hand, Yahoo does pretty much everything with Hadoop. They even built their search index with it, as I mentioned earlier. And their biggest cluster is, they have 25,000 computers with 100,000 CPUs. And that's numbers from 2009 or 2010. So it's a lot more now, probably. Or maybe not, because Yahoo is, well, I'm not going to say a sinking ship. But the biggest cluster they have is, they have 4,000 nodes, okay? And 2 times 4 CPU cores each, and 16 gigabytes of RAM. I think this is the cluster they use to win the tera sort. So we sort a terabyte of data in the smallest amount of time possible. After which, a lot of people started, like, you know, university people with beards said, but it's not efficient, like, you need so many computers, and the algorithm is, But this misses the point, right? Because you can't scale it up. This is the, of course, like, sorting a terabyte of data, Hadoop is not an efficient thing. You can easily have, I don't know, 25% improvement, 50% maybe, if you did it, like, with custom code, you know, tailored to the exact amount of data that you have at a given point in time, but you can't easily scale it up. You can't add computing nodes to make it faster, to cope with more data, with higher loads. So, yeah, they won this terabyte sorting competition with such a cluster. So of course, it's fast, but they could easily double the performance if they just doubled the number of computer nodes, right? I'm getting a call. Not anymore. And 40% of these jobs run using a system called Pig. You know, earlier Facebook uses Hive, which is SQL-like. Pig uses a language called Pig Latin, and you write processing tasks. Essentially, you give just line-by-line instructions on take this data, split it up by tab, then put it into, I don't know, these and these fields, and then use these and these fields and group them and blah, blah, blah. So you explain step by step how you want your data processed by the Hadoop system. And again, it takes these instructions, generates code out of them, and, well, creates a task in Hadoop and starts it across your processing cluster. A few other notable users would be Twitter. They use it for storage, logging. They use Pig a lot. Rackspace mostly has Lucene and Solr for log analysis. So the results get put into Lucene and Solr so they can search over it. The results of their processing jobs. LinkedIn uses friend suggestions, so they analyze the social graph with MapReduce and then produce the recommendations. Why is this always advancing two at once? Last.fm does its charts like this, which is it's the perfect use case, computing charts, because you simply count the number of times a song was played, and that's it, basically. And also A/B testing, so they log the data, and they also log, like this was feature variant A, feature variant B, and then they figure out, okay, so with this feature we had more users, like with this version of the feature we had more users, and then they figure out how to improve the usability on their side. The New York Times did a very interesting thing. They had 4 terabytes of scans of old newspaper issues, and they used Hadoop to essentially just, you know, have a huge parallel cluster of. They used Amazon's EC2, and they had these. They ran OCR software, but like on 1,000 instances or something. So this is Hadoop, which is really awesome, really convenient. It gets so many new features and bug fixes every day. Yahoo is a big contributor to Hadoop, but also other companies. Facebook uses it a lot. Facebook is very active very much involved in the Hive development, for instance. But there's one problem, which is that you need to write Java code. So what we have to do is use Hadoop's streaming feature. The idea is that it uses any kind of script as the mapper and reducer instead of a Java class. I showed you PHP code earlier. You'd have to write it in Java. But you can also have PHP. It simply starts a process and then uses, you can also configure it, blah, 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 but it uses standard in and standard out. So it simply invokes a PHP script once for the mapper and then just sends it lines of stuff. And your mappers then are expected to accept, typically, well, this is actually an old version. I'm sorry. I can't fix this now. I'll fix it before I upload the slides. It needs explanation. But it used to send the byte offset of the text file it read, tab, line. Now it just sends the line. And then your mapper is expected to produce a key, tab, the value, new line. So IP address, tab, number of bytes, new line, that we extracted from this line of Apache logs that we received. And the reducers then get key, which is the value each, and it does not start a new reducer process for a new key, so you need to watch out, okay? But there is code that takes this off your shoulders, so you don't have to deal with these aspects of it. I'll show it later. HDFS is one of the core things of Hadoop is its distributed file system, and it stores data in individual blocks. This is something that's very important because you need copies of the data across your computing clusters so you can actually send the processing jobs to where the data is, right? The default block size is 64 megabytes. You can configure this, but it's important to get as close to that as possible. If you have small logs, it's probably easier to aggregate them somewhere first. This is again where Cloudera's Flume would come in handy. Or you should group up log files because if a file you store in this HDFS is just 1 megabyte, it'll still consume 64 megabytes of disk space because this is the block size HDFS has. And the reason why it's 64 megabytes is that it's kind of the sweet spot where most hard drives really kick into their sequential reading mode. And they are allocated in blocks, so when you read these 64 megabytes, the disk is just reading. The head is moving barely as the disk spins. You don't have many seeks because seeks are slow. You're I/O bound again, so you want to stream data as much as you can. It's designed for very, very large data sets. You can store terabytes and petabytes of data in a distributed file system without issues. You can simply add nodes, and you'll increase your storage. And 64 megabytes is the reason why it's designed for streaming rather than random reads. It's write once, read many, although now appending is also possible. Initially, it was designed as you can only write a file once. If you want to append to a file, you need to read it, append, put the whole thing back. And it can do compression transparently, which is really cool. So you store something, and it's transparently gzipped, but when you read it out again, it's just text again. A few of the core concepts, I've already mentioned this, the large blocks that minimize seeks, right? The blocks are stored redundantly, so by default you have 3 records of each chunk of data. So storing 64 megabytes on disk across your 3 times 64 megabytes. And it's aware of the infrastructure, as I already explained. Each node that holds data is called a data node. Very clever. So this is storage, right? You can put this on any computer you want. And then you have a thing called the name node. The name node is, in an HDFS cluster, it's a really critical component. If you need to rely on this stuff in production, you should have failovers for that. It's all possible. It's just, this is a bit of a pain to keep up and running because the problem is that the data node, essentially the data nodes are stupid storage. They are not even aware what files are on them. If you want to read a file, you need to ask the data node, hey data node, I want to read this file, can you tell me where it is? And it'll say, it's on that computer offset such and such, and then you can read it. Which also means that the name node needs to know about all the blocks, all the files stored across your entire cluster, and I think still the entire file system tree essentially, so the info about every file and where it's located, needs to fit into memory. So a big cluster needs a name node with lots of RAM, which is another reason why you should be as close to the 64 megabytes as possible, because many small files mean that the name node will quickly fill up with just little junk files that it needs to manage. Whereas if you have bigger files, because you aggregate log data before you write it, you get a better bang for the buck, essentially. So when it's time for Hadoop to process a data job, okay, how does it work? Pretty much like I already described, because it's just MapReduce, right, which is awesome. The basic rules are it uses a so-called input format, which you can configure to split up data into single records. So you can have like a text input format, so it knows, okay, so this file has like 10 million new lines, so I can spread it out across 10 computers. 10 computers each read 1 million new lines or something. So it can even store the file when it stores them. It can split up the file and put parts of the file on different places in the cluster. There's a way of optimizing things. What I've explained earlier, when we count the number of bytes, what we did is IP address, bytes, IP address, bytes, IP address, bytes, right? And then we would ship all the identical IP addresses to one reducer instance. But that's actually inefficient because we would have 10,000 instances of the same IP address and a number of bytes. What we can do is on a mapper, like on one computer that does the mapping for a part of the data, we can already reduce, right? We can take the number of bytes and sum them up, and then to the central reducer, we only send one IP address instance and the sum of bytes. Of course, it's not possible in all circumstances. You can do this when you want to sum up something, but if you want to compute an average, doing that would, well, ruin the results, obviously. You can control the partitioning of the map yourself. So you say, okay, so the mapper gets this and this input, and the keys are, like I have key tab, key tab, key tab values. So the keys consist of 3 elements, but only the first 2 are needed to group stuff together, etc. So you can really fine-tune your processing jobs so they get the best performance. This, however, is rarely useful because typically it just takes the keys, makes a hash, and decides what reducer to pass it to. But sometimes it can make sense. And there's also a million other config options, but they don't really matter. And if you ever wondered where Hadoop got its name, it's a child's word, because this guy, Doug Cutting, who founded the project, his son, I think, had a stuffed yellow elephant, and the kid called it Hadoop, and that's why Hadoop is called Hadoop. Now, I mentioned earlier that this whole streaming stuff, you get a key tab value, another key tab value in the reducers, so you need to, new key, and then start the reducing all over. That can be made easier. There's actually no toolkits. You typically write it yourself, but I've written one. So Hadoop PHP is a little framework to help with writing MapReduce jobs in PHP. And it takes care of the input splitting for you. It does the basic decoding for you. And essentially, it simply then invokes a map and a reduce function in a class you define, and that's it. It makes it very convenient. The next version will also use an iterator rather than grouping up all the values for a key first, because that's much more memory efficient, but that's just an implementational detail. But the really cool thing it does is it packages your job as one FAR file. Because what you need to do is when you have, let's say you have 100 PHP classes because you have a really complex processing job, then you need to tell Hadoop, streaming, and here's the first file you need to package and send to every computer. This is the second, this is the third, fourth, fifth, and so forth. And then invoke this command, which is a complete pain. So this just makes one little FAR file that contains all the code needed to do the data processing, and then also creates a simple file that'll invoke Hadoop and ship it out to different computers. So you write a mapper class, you write a reducer class, maybe you set some options, then you run this compiler, and it'll create a shell script for you. You run the shell script, and that just, boom, starts the processing. It is, as I said, written by me. I wrote it, however, yesterday and this morning. But it's still going to be awesome. I'm German, right? So it won't let you down, and it'll still work in 1,000 years. Unlike a PHP, like a French implementation of this would probably surrender. Because it says, oh, too much data. So this doesn't exist yet. I need to upload this later because I had problems with the stuff this morning. I wanted to I needed to document everything like dutifully. Every method needs a full signature API docs and stuff because it's German. I can't help it. It's my OCD. So, but I'll hope this should be online this afternoon. And with this stuff, this untested code, I'm now going to do a hands-on. I have to sync the screens. Okay. So let's, I'll show some basics first. We have,
Do you think you can increase the fault delivery?
absolutely.
It's fine for me then.
I'll do a general setting. Is this better? Yeah, but I have to do it on every file, so I'm doing a central. Is this readable for everybody, or still too small? I was asking the people in the back, Derek, not you. Can you guys see this at the back, or should I make bigger? Yeah, no complaints? So this is like the basic configuration that you need for Hadoop. You simply download Hadoop. I typically go to a site called cloudera.com. It'll be on the last slide in the further reading section. Because they have a distribution for Hadoop that simply you download it, you extract it, and you're ready to go. And they keep adding patches to Hadoop, and they make regular releases, and they have lots of extra software like this Flume thing for aggregating log data and getting data into this Hadoop distributed file system. So you download this, then you extract it. You add, this is in the quick start guide, so you don't have to write this down or something. You simply say, okay, I have one job tracker locally. I have one name node locally, just one replication factor 1 because I have just one node for data, right? So I don't need a number for 3. And the core system needs to know that the file system is located here. And then you can simply start it. I actually have it already running. You should run this Hadoop env, I think, or Hadoop start all. There's a script. And that starts a name node, a data node, a job tracker, everything. So you have a distributed file system running locally. You have the job tracker. Everything runs locally. It's called the pseudo-distributed mode. It's not actually distributed because it is just one machine. But yes?
Can you use a different port, please?
Why?
Because it uses the same as XDebug.
It's the default port. I'm sorry. Change your port.
No, I was first.
But Hadoop is bigger than XDebug. No?
It's in Wikipedia already, too.
Oh. Okay, I don't know how to change this setting. So. It's good I'm not running XDebug. Because I hate it. Because I don't like it. It's Dutch. Why would I use it? So, shell, and there's lots of, I'll need this documentation later. Because, yeah. Okay, so to demonstrate that there's something running here, this is as big as I can make it. That's what she said. Sorry, I'm sorry. So we have Hadoop something running here, which doesn't really matter because I have a $Hadoop home set. And if we run this, we can run the file system, bin Hadoop file system list. There is nothing because my user doesn't exist. One thing you need for this mode, you can also have a purely local mode, but there's not as much fun because it doesn't really start like a name node and all the stuff. All you need before this is your local user needs to be able to SSH to localhost. So you need to add your own key to allow, authorized keys, but that's it. So here we have a test1 directory. And there's an input file. We can just cat this. There's Hadoop home bin Hadoop fs cat test1. I think I called it input app access log. Yeah. So this is essentially one file. One big file is like 5 megabytes or something with my local code. As you can see here. Yeah, there's not a lot of stuff in there, so it's not going to be that entertaining to work with, but at least it works and it has some data. We have here, oopsie, This is on 5030 and on 5070. You'll have web interfaces that give you basic statistics for the system that you're running. So here we have the name node. Oh, I'm sorry. Here we have the name node. If we refresh this, we can also browse the file system from inside the browser. Here's test 1 and so forth. So this is the file system, right? This is the access log. We see we have 5.59 megabytes utilized, etc., blah. And we have just one data node live. In a bigger cluster, it would be more. And this is the MapReduce status interface. There is no tasks running right now, which is what we want to change. So we'll try and see if this works. God damn it. So the problem is I've written this code before. Like I've given this a similar talk before, but it wasn't as good like the code that I wrote. So and in the meantime, for a bunch of clients, I also improved like this basic framework. And then I said, hey, I should really open source this, don't you think? And they said, yeah, why not? And so this is what I started doing like yesterday. But it was more complex than I imagined it to be, like changing all the file names and changing a bunch of things around. So what we have here, I'm sorry, I'm actually going to use this shell because it's already the right directory. So I have OSS, and I called it Hadoop PHP. Why is it not there? Oh, it is there. I don't have Symfony on my hard drive. You didn't see that. Stupid Symfony. So you have an example, a hit counter, okay? Here's the mapper PHP file, and here is the reducer. The mapper simply uses a method called parse Apache logline, and it emits the request URI and a 1 because it's one hit, right? We could also use the number of bytes here. This is something that is actually bundled, so parsing an Apache logline is in a util class. Now, we can try and run this locally if this was in the include path, but we can simply compile it. This is the examples directory, and in bin, you'll have a compile PHP. So we can theoretically run, go to the examples, hit counter, run PHP on compile PHP. Where is it? So it'll tell us we need to provide the path to the jobs folder, which the map has the map and reducer file, and we need to tell it where to generate the var and the shell script to. We can also do -i and then some sort of path, and it'll import that whole tree into your var file as well. So when you have like classes with generic code that you use as utilities, you can say include this in this var package. I have not tested that, so I don't know if it works, and we don't need it. But we can say, because we're in the hit counter directory, use the local input and add generated locally, which is a stupid idea, as I just realized, because it'll include these files as well, so it grows bigger and bigger every few minutes. So let's do it here. So now we have a hit counter.var and a hit counter.sh. Change mods. The shell script might actually not work, because here's the problem. If I do this, it just gives me a bunch of question marks because of the stupid detect Unicode feature that nobody understands. Derek, would you like to comment? This happens when I run a var file. Do you see what happens? No. It prints a bunch of question marks. What I need to do is minus detect Unicode off or something. Hold on. Yeah. It does. It's 533. Yep.
Version, but does the job. And we... not anymore with version 2.6. You can do it with ANT.
Huh? I know. I didn't say it either. So. Maybe. Hey. So, Good for you guys. Apparently that made people happy over there. Okay, so they're cheering. So we can try now is I'm simply going to cat var log Apache to access log and pipe it into this. Ah, stupid trackpad. Oh, that's not working. Oh, actually it is. Yeah. So let's see. Hit counter mapper. It's supposed to read the request URI, but it's not really. Let's try this. Yeah, that works. So there's a bug in the script. It extracts the wrong thing. Hold on. Sorry, what?
In the script, you're using value, not log.
Am I?
Yeah, on reducer. In the emit, you were using value thing. I guess you want log.
Oh, yes. Thank you. Thank you. Awesome. This is like, it's good that you guys haven't fallen asleep. Good. Great. Great success. So, hit counter, okay. And we can recompile this. Boom. And give it another shot. No. Why? Why is it not working? Are you going to believe me when I say it worked before? It's like, yeah, maybe. Damn it.
Maybe you need some Dutch software to help you.
There should be a request URI. So I don't know why it doesn't work. It might be that this is actually, oh, yeah. Oh, yeah. So I think this is actually modified to read Nginx log files, which are slightly different. So it's returning false, or it's returning null, and it can't read stuff. Okay, I don't know, we need to do something else, like emit. Yeah. Like between 0 and 1. And can we somehow, I don't know. What? Oh. And I need to recompile it. Yeah, that sucks. Because I kind of... Okay, that works. Pretty lame too. If I do 0 and 5, is it gonna integers? Gonna be integers? What is he saying? Nothing. Why do you always sit in my talks and don't pay attention, Derek? Seriously, I find it offensive. It's boring, did you say? Your mom is boring? Okay, so this is working. This is working. So let's try and run it on the distributed file system. I don't know if that works. I need to edit this. So what it creates this, okay? So you provide it with an HDFS input directory and an output directory. It'll also see, is there a Hadoop home defined? If not, it assumes like a standard value. And you see this, the mapper and the reducer actually already has the detect Unicode off, because in the directory here, I also put a file called arguments. Typically, you don't need this. So if you have a PHP installation that works with, even though the detect Unicode is broken, that would work. In my case, I have to override the mapper and the reducer thingies, okay? I could also here define other Hadoop streaming options, like don't use tab, but use a comma as a separator or a space character for keys and values, or the key is actually a value tab value, and then only the value starts after another key tab value, something like this, stuff like that. It's all in the streaming documentation. So theoretically, this should work. Hit counter, and our input directory was, if I remember correctly, test1 input, and we want to have it in test2 output. So it's actually not working on the, it's using random numbers now, but. Oh, and in the meantime, we could, boom, here. Oh, the map is complete, but it's reducing still. So I'm only running one mapper instance and one reduce instance. So this is not technically distributed data processing with PHP. I'm sorry. So I was lying to you. Okay, so Hadoop FS list in test 2. Oopsie, did I really test 2? Well, whatever. Yep, and there's a part 000. And we can cat this. Damn it. Okay, one last straw here. What we can do, this is actually pretty cool. Instead of having a reducer that is written in PHP, we can use a native Hadoop reducer. And what we do is we cheat. We say, make a long value sum. And in arguments, we say reducer aggregate. And that's it. So I'm going to try and recompile this. There must be something wrong with my reducer for some reason. Hadoop home bin, just need to compile it. Does it still have executable permissions? Yep. So in this case, we can do test 1 output. And I hope this will work. In the meantime, I can figure out what is wrong. I realize we're running over time. I know. I'll be right done. Return an array sum of values. Maybe I have to emit the array sum of values. Let's see. Handle. Yep. I have to do $this emit. That'll fix it. But maybe. Please work, please work. Yeah! Awesome. So it's not really random. There's quite the, yeah. Okay, so whilst I do this, is there any questions right now? Yes, please.
So all the examples that you've mentioned are basically about processing data that's text data that's on HDFS. Does it make sense to use MapReduce? Like, say I have lots of data in a central database and use mappers to connect to that database? And
no, because then, well, you can. There's nothing stopping you from, like, in the mapper process, opening somehow a connection to the MySQL database. But the problem is that you have then 100 nodes accessing this data, and you're I/O bound again. What you do in this case is you use a utility that these Cloudera guys, there's going to be a link in the next slide, wrote. It's called Scoop, and it allows you to extract a table or a part of a table and put it into HDFS as text files, like with tab separation, or even as a Hive table. And then you can run queries on that or MapReduce jobs on that. So what I've done mostly for my clients is written basic MapReduce tasks that use either, one thing is log files typically from web service, and the other thing is stuff that an application logged, for which I use JSON. So you'd simply log a line of JSON to a file, and using this Cloudera Flume thing that then buffers stuff up until you hit a few dozen megabytes, and then it writes it to a distributed file system. And then each mapper just takes the input, runs JSON encode over it, figures out, aha, so this is this kind of event, this is that kind of event, and then acts accordingly. Because you don't know what is in the log file, right? It could be random log files. And then basic processing jobs take this JSON stuff and produce intermediary records with this. So maybe they just transform the JSON to something like key tab value, or maybe they do some sort of aggregation. And then this intermediary result is stored locally, because maybe that happens once a day. And then you can load a whole month of data, which is already pre-processed, into Hive, and just run a simple select query. You go like select from all the month tables and group by day and count the number of hits. And then you see like the number of hits. And then you can load that into Excel and make a nice pie chart. You can even, Hive even has a JDBC and an ODBC interface, so you can use like Crystal Reports or other reporting software and connect to Hive and run SQL queries on this thing. It'll take a few minutes, a few hours, but it'll eventually get back to you. So this is pretty cool. Yes, other questions? Does this answer your question? Yes.
I think we will have to put the other questions offline and just wrap this up. Yeah.
Okay.
Cheers.
That's fine. Let me finish the presentation slides. There's not a lot of stuff. I'll hurry. Little tour. Apache Avro, I've mentioned, is a data serialization format. In the streaming stuff and like actual implementational stuff doesn't use that. It's just used something that they use a lot. Cloudera Flume is this log aggregation software. So if you run Scribe, get rid of Scribe, install Flume, you can say on each server there's a local agent that buffers stuff and occasionally sends to a collector tier, which then sends it further down, further down, further down. So it really scales really well. You can say this log message must be written to the file system to like 10 computers away before it returns. Or you can do it completely asynchronously, like as a best effort thing. It's awesome. It's super scalable. It works. It's extreme. It's rock solid. That's great. HBase is kind of maybe you've heard of Google's Big Table. It's a big table implementation. So if you want to analyze your data that way, you can. HDFS is a distributed file system, which is you could use it for other purposes, storing images in a distributed fashion. Hive is an SQL interface. Pig is this processing language. Zookeeper organizes your distributed applications if you want. So this is projects that parts of MapReduce uses or Hadoop uses. Sometimes it does, sometimes it doesn't. But it all fits into this parallel processing stuff. So there's lots of software to leverage from, and use from this ecosystem. That would be the end. This is a bit of further reading. This is a really good tutorial. The Cloudera guys have this distribution for Hadoop. It's really easy to install. It comes with Hadoop, with Hive, with Flume, everything. You just need to